Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module measurements and the statistical treatments from the paper Measurement and Instrumentation. From this module, students may get to know about the following methods: the measures of central tendency, measure of dispersion from the mean, which includes dispersion, range, deviation, average deviation, standard deviation, variance, normal or Gaussian curve of errors. Students will also learn about the precision index, probable error, standard deviation for the normal curve, and mean. At the end, students will get to know about the standard deviation, which will include specifying measurement data, uncertainty analysis, and treatment of single sample data. Also, propagation of uncertainties. Students, as we know, to get highly accurate value of the quantity in a measurement, the tests must be performed using as many different techniques, procedures, and experimenters as possible. Without going into details of the statistical methods and their mathematical backgrounds, we will consider only those aspects which are of importance to us in processing of data. First, we will learn about the measures of central tendency. Statistically speaking, a central point or average is a value which is typical or representative of a set of data. Since the average tends to lie centrally within a set of data arranged according to the magnitude, it is called the central point or a measure of central tendency. Generally, 6 types of averages are defined. They are mode, second median, arithmetic mean or simply mean, geometric mean, harmonic mean, and root mean square. So students, now let us see the 6 different type of averages one by one. First, mode. Mode is defined as most frequent value. The mode may not exist, or even if it does, it may not be unique. Second, median. Median is the value below which half the values in the sample fall. Third, arithmetic mean. The most plausible value of a measured variable or variate is the arithmetic mean of the several readings acquired. The best estimate is made when a large number of samples or readings of the same quantity are taken. Theoretically, an infinite number of samples would provide the most accurate result. However, in practice, only a finite number of samples can be taken for a given quantity. The arithmetic mean is given by z bar is equal to z1 plus z2 plus z3 so on up to zn divided by n, that is summation of z upon n, where z bar is the arithmetic mean, z1, z2 and so on up to zn are the readings or variates of samples, and n is the number of readings. Now let us see the geometric mean. Geometric mean of a set of n numbers x1, x2, x3 up to xn is the nth root of the product of all the numbers. Geometric mean is given by GM is equal to the nth root of the multiplication of all the numbers x1, x2, x3, so on up to xn. Now, the harmonic mean. Harmonic mean of a set of n numbers x1, x2, x3 up to xn is the reciprocal of the arithmetic mean of reciprocals of the numbers. Harmonic mean is given by hm is equal to 1 by n summation I equal to 1 to n 1 by xi, where n is the total number of numbers. Next, root mean square. Root mean square or quadratic mean of a set of n numbers x1, x2 up to xn is defined as RMS is equal to square root of summation I equal to 1 to n xi square divided by n. Now students, let us see the measure of dispersion from the mean. First, dispersion. It is the property which represents the extent to which the values are distributed about the central value. The terms like spread or scatter are also used to denote dispersion. Consider the figure as shown, which shows two sets of data. In one case, that is the curve 1, the values vary from x1 to x2, and in the other case, the values vary from x3 to x4. However, the central value of both the curves is same. From the figure, it is clear that the dispersion is lower in curve 1 than that in curve 2. Now students, let us see the deviation. The observed difference of a reading from the arithmetic mean of the group of readings is called deviation. Let the deviation of reading R1 be D1 and that of reading R2 be D2, etc. Then D1 is given by R1 minus R bar. D2 is given by R2 minus R bar. D3 is given by R3 minus R bar. And in a similar way, Dn is given by Rn minus R bar, where R bar is equal to summation of Rn minus Dn divided by n. If we take the sum of deviations d1 plus d2 plus d3 plus d4 and so on up to dn, we get r1 minus r bar plus r2 minus r bar plus r3 minus r bar and so on up to Rn minus R bar, which gives R1 plus R2 plus R3 up to Rn minus n multiplied by R bar, which is nothing but equal to 0. Since we know by the definition of R bar that R bar is equal to R1 plus R2 plus up to Rn divided by n. Next is the average deviation. The addition of the absolute values of deviations divided by the total number of readings is defined as average deviation. The absolute value of deviation is the value without respect of its sign. The average deviation provides an indication of the precision of the instruments used in making the measurements, with highly precise instruments yielding a low average deviation between the readings. Average deviation may be expressed as capital D is equal to mod of D1 plus mod of D2 plus mod of D3 plus and so on up to mod of Dn divided by n, which can be written as summation of mod Dn divided by n. Now students, let us see the standard deviation, which may be written as SD. Standard deviation or the root mean square deviation is also a very important expression in the analysis of random errors. For infinite number of data values, the standard deviation is defined as the root square of the addition of the individual deviations squared and divided by the number of readings. Thus, standard deviation may be expressed as SD is equal to sigma is equal to square root of D1 square plus D2 square plus Dn square divided by n, which in short can be written as square root of summation di square by n. Next is variance. The variance is defined as the mean square deviation. It is similar as standard deviation, only that square root is not extracted in it. Thus, variance is given by the expression V is equal to square of standard deviation, which can be written as sigma square, which is equal to summation di square by n. Next is normal or Gaussian curve of errors. Random effects are mostly studied by the normal or Gaussian law of errors, and this type of distribution is generally encountered in practice. By the law of probability, one can write the normal occurrence of deviations from their average value of an infinite number of observations or measurements as follows. Y is equal to h by square root of pi multiplied by exponential minus h square x square. Let us represent this equation by equation number 1, where x is the magnitude of deviation, y is the number of readings at any deviation x, the probability of occurrence of deviation x, h is the constant called as precision index. Equation 1, when plotted, leads to a curve as shown in the figure. and is called as normal or Gaussian probability curve. This normal probability curve is always symmetrical about its arithmetic mean value, and area under the curve is always unity. Consider a situation where we have a large number of measured readings n. Then the probable number delta n having a deviation in between x and x plus delta x is given by delta n is equal to n multiplied by y into delta x, which is given as n into h by square root of pi multiplied by exponential minus h square x square delta x. Let us represent this equation by equation 2. Integrating this equation number 2 from minus infinity to plus infinity, we would be dealing with all the probable cases. So, this expression n multiplied by h by square root of pi integration minus infinity to plus infinity exponential minus h square x square delta x is equal to n. Let us represent this by equation number 3. Therefore, h by square root of pi integration minus infinity to plus infinity exponential minus h square x square dx is equal to 1. Thus, the integral of y from minus infinity to plus infinity is equal to unity, and the total number of readings occurring between x1 and x2 would give the area under the curve between these values. Thus, n12 is equal to h by root pi integration minus infinity to plus infinity exponential minus h square x square, where n12 is the total number of measurements made between the values x1 and x2. Generalizing the probability to find a deviation in between x1 and x2 is given as probability of x1 x2 is equal to h by root pi integration minus infinity to plus infinity exponential minus h square x square dx. So students, the measure of dispersion from the central value is very important, as it is an indication of the degree of consistency or precision and regularity of the data. A large dispersion in the measured data is not desirable, as it represents that some factors involved in the measurement process are not under proper control, and therefore it is difficult to estimate the measured quantity with full definiteness. Thus, if we have two sets of data with two different dispersions, then we can rely the data with less dispersion more than the one with higher dispersion. Dispersion can be defined in terms of several terms as explained. First, range. The difference between the greatest and least values of data is called as range, which is the simplest possible measure of dispersion. For example, in the figure, the range of curve 1 is x2 minus x1 and that of curve 2 is x4 minus x3. Now students, let us see the probable error. The arithmetic mean of the various measured values gives the most probable value of a Gaussian distribution. Also, it has been shown that the estimation of most probable value is related to the sharpness of the normal distribution curve. In the figure, 2 points minus r and plus r are being marked. The position of these points is such that the area bounded by these 2 points is equal to half the total area under the curve. This means half the total deviations lie in between x is equal to plus minus r. The location of r can be simply observed as h by square root of pi integration minus r to plus r exponential minus h square x square dx is equal to 1 by 2. That is, r is equal to 0.4764 divided by h. Now, let us see the standard deviation of the normal curve. We know the standard deviation is given as sigma is equal to square root of summation di square by n. Thus, for a normal distribution curve, standard deviation is given by sigma square is equal to 2h by square root of pi integration 0 to plus infinity exponential minus h square x square multiplied by x square dx is equal to 1 by 2h square, or the standard deviation for the normal curve is given by sigma square is equal to 1 by root 2h, which is equal to r by 0.6745. Next is the standard deviation of mean. In order to handle multiple sample data, the mean value of various sets of data can be investigated by statistical means, which is done by taking standard deviation of the mean. The standard deviation of the mean is given by sigma m is equal to sigma by root n. Next is the standard deviation of standard deviation. For a multi-sample data, the standard deviation of the standard deviation is given as sigma subscript sigma is equal to sigma by square root of 2n. Now students, let us see the specifying of measurement data. The results may be specified after performing the statistical analysis of multi-sample data. Generally, the results are represented as deviations around a mean value. The deviations are expressed as first, standard deviation. The result is expressed as x bar plus minus sigma. Second, probable error. The results is expressed as x bar plus minus 0.6745 sigma. Third, as plus minus 2 sigma limits. In case we want to increase our probability range, we would specify the results as x bar plus minus 2 sigma. Fourth way is plus minus 3 sigma limits. In case we wish to increase our probability range, we would specify the results as x bar plus minus 3 sigma. The maximum or boundary limit is plus minus 3 sigma. The probability in this case is 0.9974. This means that 99.74% of the observations will fall within this limit. In other words, we can say that there is a possibility of only 26 readings out of 1000 to fall beyond this limit. Thus, practically all the observations are included in this limit. The odds of any observation falling out of this limit are 256 to 1. So students, let us see the precision index. If deviation x is equal to 0, then from equation 1 we get y is equal to h by square root of pi. Hence, the maximum value of y depends upon h. The probability curve would be sharper for higher values of h. Hence, the value of h determines the sharpness of the curve. A sharp curve indicates that the deviations are closely grouped together around x is equal to 0. Larger value of h represents high precision in data, as the occurrence probability in a given range falls rapidly as the deviation increases, since the variates cluster into a narrow range. However, smaller h represents lower precision, as the occurrence probability in a given range falls off gradually with the increase in deviation. So students, towards the end, let us see the propagation of uncertainties. When several variates are involved in a measurement, the uncertainty analysis is done on the similar to the error analysis, where the results are represented as standard deviations or probable errors. Let us suppose x is a function of several variables. X is equal to function of x1, x2, x3 up to xn, where x1, x2 up to xn are independent variables with the same degree of odds. Let Wx be the resultant uncertainty and Wx1, Wx2, so on up to Wxn be the uncertainties in the independent variables x1, x2 up to xn respectively. The uncertainty in the result will then be given by Wx is equal to square root of del x by del x1 whole square Wx1 square plus del x by del x2 whole square Wx2 square and so on up to del x by del xn whole square Wxn square. Now students, let us understand the uncertainty analysis and treatment of single sample data. Several times, only the single sample data is available, and hence the statistical methods discussed so far cannot be applied directly. A method has been proposed, which is based upon probability and statistics, and it analyzes the data employing uncertainty distribution rather than frequency distribution. The single sample result can be expressed in terms of a mean value and an uncertainty interval with given odds, where the result may be written as follows: A is equal to A bar plus minus W, B to 1, where A bar is equal to the value if only one reading is available on the arithmetic mean of several readings, and W is the uncertainty interval. Here B represents the odds or the chance that the true value lies within the stated range based upon the opinion of the experimenter. Consider the following example, which explains the uncertainty analysis. The results of a temperature measurement may be expressed as T is equal to 100 degrees Celsius plus minus 1 degree Celsius, which means that the uncertainty in the results is plus minus 1 degree Celsius. That is, the experimenter is sure about the precision of measurements which he has made in the range plus minus 1 degree Celsius. These results may be expressed as T is equal to 100 degrees Celsius plus minus 1 degree Celsius 20 to 1, which makes the results more specific in nature, as the experimenter is now claiming that there are 20 to 1 odds that the temperature measurements are correct within plus minus 1 degree Celsius of 100 degrees Celsius. So students, let us summarize what we have learned in this module. We learned about the measures of central tendency, which included mode, median, arithmetic mean or simply mean, geometric mean, harmonic mean, and root mean square. Next, we studied the measure of dispersion from the mean, which included dispersion, range, deviation, average deviation, standard deviation, variance, normal or Gaussian curve of errors. Thirdly, we studied the precision index and probable error. Next, we studied the standard deviation for the normal curve, mean, standard deviation, which is specifying the measurement data. We also studied the uncertainty analysis and treatment of single sample data. At the end, we studied the propagation of uncertainties in this module. Thank you.